And you can talk about the distance between true probability distribution and the distribution you learn. And there are ways of computing probability distribution distances, and it's actually the cross-entropy distance. I mentioned this at the time of neural networks and logistic regression. But we'll get to learning soon enough. So I want to do two things right now. Any other questions? Good, thanks for the questions. I think that tells me that. But now I'm just going to continue this. I gave you now the numbers finally. Remember this thing I said, the numbers are but a crutch. You can do a lot of thinking without numbers. You did all that stuff without knowing what the heck are those numbers. All the things that I told you are true irrespective of what I put as the numbers here. Now I put the numbers. Now tell me what that joint distribution entry is. And while you're doing it, I'm going to set up a code. Okay, so think about this, and I want to tell you the code that I'm going to set up. This is related to your life. This is accounting life. This is stuff that you want to understand. There is mundane life, such as exams. So I have a question about exams. For the final, I'm going to take the code right now as a short answer code that will also work out as a kind of maintenance. Okay, so I have to take maintenance specifically. I have two options for you. One is you can do an in-class exam the usual way at the time that the university has given, or I can give you a take-home. Okay. Right? So while you're doing this, think about that, and I'm going to open the phone and just say whether you want in-class or take-home. Okay? That's it. Yes? It's just, all of those will be taken care of. Okay? So you have to tell me, without knowing all exact details, will I do well in the take-home versus final? I can't answer that. Yes.
I was going to ask.
Will I do well in the take-home versus final? I have no idea. Okay? You make life decisions, with information that's available. And let me tell you what my preference is, and I'm sure it's also the TA's preference in class. Because as I say, empty sheets are so much easier to grade. Okay, people tend to put up a fight when they have a take home. And then they get mad at me, saying, oh, I spent so much time trying to understand. Well, I'm sorry. You could have just acted as if it's an in-class exam, given yourself exactly, whatever, 1 hour, 50 minutes, and given me the empty sheets. It was your self-respect that somehow coming into the way. So don't yell at me because you have self-respect. You see what I'm saying? So you can take home as an in-class. You can even come here and maybe there will be people and stand, But if I do a take home, it will just be a take home. It will be given at a certain time and it will be due at a certain other time. Yes?
Will we make it more difficult because we'll have more time?
No answers of that kind will be provided. No, if it is take home, normally I would require hard copy, but I take into account hardship situations. If people are in travel, I allow for like scans. Final is final. I haven't decided that. Okay, so I'm going to open this. So would you take home or in-class final? One time, start. Are people able to see that?
That's
Okay, I'm going to show it a little bit just so that you know that I'm not making up what I will say. And then I'll tell you the actual results. Actual results, you know, after evaluation. We have 72 answers currently. And it seems to be mostly different. I didn't count, it seems to be mostly different. Okay. Okay. So, that's that. Let's go back to the life. Can you remind me 10 more minutes? I'll close the phone.
Okay.
Okay, so let's see what is this number. Do people know this number? What is the number here? You know, remember, use these kinds of numbers to say you can compute the joint distribution. So somehow that network should be giving that number. Right? Imagine, it's also true for any actual network. Actually, imagine if it is this network. And I just said this is 0.5, 0.3. So this is like cloudy. And this is sprinkler. This is drain. And this is wet grass. And I said this is 0.5, 0.3, 0.9, 0.4. I just made these numbers up. This, remember, I'm a basic. I can make up numbers as long as I'm consistent with this use of these numbers. I'm fine. Okay? So if I were doing this as the network, and again, please understand that that is a network. Remember that network doesn't mean it must have edges. It can be a completely disconnected network. Okay, so what would this number be? It would be cloudy. So this is a P of A, B, C, D. It would be P of A times P of B times P of C times P of D. Right? So it would have been, in this particular case, it would have been cloudy is 0.5 times not sprinkler is 1 minus 0.3 times times the rain, I need rain, so 0.9 times not wet grass is 1 minus 0.4. That's a number. So that is the number corresponding to this joint distribution if that is your network. Now I want to know what is the number corresponding to this network. Okay, so what is it? So I just basically, in essence, you can write this in the reverse topological sort first. Okay, write it as probability of not wet grass. Okay, and then rain, not sprinkler, cloudy. Because this essentially is P of A and B is the same as P of B and A. Everybody agrees on that. So then I basically, essentially, in my mind, use the chain rule. So this would have been written as probability of not wet grass given everything else. But probability of not wet grass given everything else is just probability of not wet grass given its immediate parents. Okay? So this is really, I need to compute the probability of not wet grass given rain and not sprinklers. So not sprinklers and rain. This is not sprinklers, this is rain. If the sprinkler is false and rain is true, then wet grass will be 0.9. So not wet grass would be 0.1. Okay, times. Then similarly, rain given everything. But rain given everything will be just rain given cloudy. Okay? So rain given cloudy, if cloudy is true, rain is 0.8. Then not sprinkler given everything. Not sprinkler given everything is nothing but not sprinkler given cloudy. Its immediate parent. Right? Not sprinkler given cloudy, if cloudy is true, sprinkler is 0.10, so not sprinkler will be 0.9. times probability of cloudy given everything else. It turns out in this particular case, cloudy is independent of everything else given its parents. Its parents don't exist, it's an R form. So that's just probability of cloudy. That is 0.5. Is there a number? So you can write a little program that will just spit out the 16 numbers corresponding to this probability distribution. Now, you all agree, at least you agreed last time around, that if I give you the joint distribution, you can answer any probabilistic way. You did, right? So I'm going to check whether you mean it. Okay, I'll give you a very small probability distribution, joint distribution. This is like elementary probability theory, just to make you remember. Okay, so the point is, I told you how you can go from network to the joint distribution. And if you know the joint distribution, you can answer any questions about these variables. Okay, and I want to check that you really believe this. And then the question really would be, can you answer these questions without completely enumerating the joint distribution and going up from there? That is going to be the efficiency of inference. Okay? Okay, let's see, here are some of the queries. In fact, pretty much any query you can think of will be of this type, one of these types. So this is my joint distribution over toothaches and cavities. Okay, this is a joint distribution over toothaches and cavities. Okay, so basically it says toothache and cavity. If you just take a random person, okay, the probability that they will have both toothache and cavity is 0.04. The probability that they will have no toothache but have a cavity is 0.06. The probability that they have no cavity but toothache is 0.01. Probability that neither they have no cavities, no toothaches is 0.89. You would expect that, right? Random people probably have reasonable. Okay. So this is my joint distribution. So now let's see. I asked this question: what's the probability of cavity and toothache? 4. We just pick this up, right? What's the probability of cavity? What did you do? Because cavity is true with either toothache present or toothache absent. Okay, so this is nothing but sum over toothache probability of toothache true false, cavity and toothache. You see what I just said? This has a fancy name. It's called marginalization. Marginalization. So now for a joke, right? Imagine I'm doing integration here. Have you done probabilistic reasoning both for discrete probability distributions and continuous ones? If you do continuous ones, what happens to that summation? Integration. It becomes integration. So that's why we say Bayesians are the only people who feel marginalized when they get integrated. And when you understand these kinds of jokes, you realize that you have lost your normal life. Right? So you integrate, you marginalize. You integrate away the other variable. Okay. Then, what about PTA? It's the same thing. Now you just CA for all the values, probability of CATA. Any time you sum over a variable, that variable gets marginalized. Right? So what is that? So anyway, in this particular case, this would be 0.04 plus 0.06. Right? And then this will be 0.04 plus no. What's the problem? CA. No, I'm talking about this. Probability of C. Okay? And then this one, probability of TA is 0.04 plus 0.1. 0.01. This 0.05. Let's do this one. Probability of CA given not TA. Actually, a lot of times you want to know this. I found some evidence. Some patient came in and I poked their teeth and I found they don't have, well, actually this is strange, but they said they didn't have any toothaches. You didn't even start working there, okay? They came in and said, you know, I don't have toothaches, do I have cavities? These are the kinds of patients, if they exist, doctors will be really happy. Right? Because these are the people who will come to the doctor and say, I don't have any runny nose, can you check if I have it? Okay. These are the good hypochondriac patients. And you know that your practices are made of these kinds of patients. But anyway, so CA given not TA. In fact, a more reasonable thing, equality, that's, it is probability of, yeah, sorry, okay, so, is probability of cavity given to TA. So somebody comes in complaining about toothache, and you're trying to check what's the probability that they have a cavity. Both of them can be answered with these numbers, right? So what is this one, probability CA given not here? How do you do this? This is the definition of conditional probability. Yeah, thank you. This is the definition of conditional probability. Probability of CA and not TA by probability of not TA. You understand this? This is the definition of conditional probability. So this CA and not TA, CA and not TA is 0.06. Probability of not TA, probability of TA is 0.05. Probability of not TA is 1 minus 0.05. That's the number. You believe me now, right? I mean, you believed it yourself before, but now you know that conditional probabilities can be done. Right? And you can compute the other one too. The last one I want to just ask you to think about is probability of cavity or toothache. Probability of A or B. That it turns out, basically this is probability of cavity plus probability of toothache minus probability of cavity and toothache. This is the set theoretic definition. It turns out actually everything else is just needed for probability theory to even make sense. And this rule is in some sense it's a sort of a choice. Okay, and the textbook actually talks about this beautiful argument by Definity, which says, if you don't believe this rule, then I can set up a gamble where you will lose all your money. So you can decide whether you want to believe it or not. I mean, this is the kind of thing you should do to people who don't believe in evolution, biology, etc. Right? Like, if you don't believe in it, I can get you into a situation where essentially you won't get any treatment, because any treatment based on science cannot be used for you. Would you still want to believe? Some people do actually, but most people may not. And so this is basically actually read the textbook. They talk about the interesting probability theory arguments as to why people had to go with this. But it sort of makes sense to you. And once again, you can answer that using the joint distribution numbers. Agreed? Okay? So, then basically what I'm saying is that if I give this network, then I can, any network, it defines a joint distribution, and from the joint distribution, I can answer every query. So at least from a first principles point of view, you know how to use Bayes networks. The question is whether you can do it more efficiently. Okay? Let me stop the board. So that's just basically what I showed. Okay. Now, one other thing is it's worthwhile thinking about conditional probabilities. It's actually very important to think about conditional probabilities. Because, mostly in Bayes networks, all the probability entries are conditional probabilities. right? They are called those tables. These tables, these are called CPTs, conditional probability table. They give you conditional probability. Okay, so now here is an interesting thing. Actually, I'll get to that slide in a minute, but see, right, since there is space here, I'll write it here. Notice P, A, given B is P, A, and B by PB. That's by definition. As long as B is not, probability of B is not equal to 0. Which actually means probability of A and B is probability of A given B times PB. This is what is called chain rule. A joint distribution was written as a product of conditional distributions. We used this last class. We said probability of A, B, C, D is probability of A given B, C, D times probability of B, C, D. And then probability of B, C, D is probability of B given C, D times probability of C, D. And then probability of C, D is probability of C given D times probability of D. It's just repeated application of chain rule. One other interesting thing that you can play with this is, so P, A and B. So now what about P, B and A? Probability of B given A. By definition, probability of A and B by probability of A. Right? I wrote A and B, but it's A and A and A and B are the same. Which essentially means this same probability of A and B can either be written this way or be written this way. Which actually means probability of B given A is nothing but probability of A given B times probability of B by probability of A. If you figure this out, how much recognition do you think history has to give you? This is the celebrated Bayes. So Bayes did this algebra and figured out that P, A and B can be written in two different ways, because of which probability of A given B can be written in terms of probability of B given A. Why did he become so famous for that? It seems like, it looks as if there's very little fame to be gained anymore. All the easy ones were taken by him. Okay? So the question is, why is this such a useful rule? Think about it this way. You go to the doctor with symptoms and ask the probability that you are suffering from a disease. The doctor basically has a practice to say probability that you have this disease given these symptoms. Now, what is medical textbook written in terms of? Medical textbooks are written in the other way around. They are written in terms of probability that you will have a symptom given that you have this disease. So what do medical doctors do? They go inside the room and use the Bayes rule. Come back and charge you $150. That's what basically Bayesian rule tells you. The one where you say probability of a symptom given disease, that's called the causal probability. Because you assume symptoms are caused by diseases. Textbooks are written in terms of causal probabilities. Why? Because the causal probability doesn't change irrespective of whether you are getting that number in Tempe or in Nairobi or in Pedagogy. The possibility that a particular disease causes a particular symptom is independent of where you got the data from. On the other hand, probability that a symptom indicates the presence of the disease, which is the diagnostic probability, that may very well depend on the local conditions. Like for example, if there is like a huge ice cream festival today, everybody basically having anything free overeating, right? At which point of time you will start getting lots of toothaches. Does that increase the probability that you have cavity? No, it's just toothache because of ice cream. You understand? And so that is the kind of that reasoning that Bayes' rule helps you do. And so even though it looks like an extremely silly rule which just changes the order, from one side to other, it's actually extremely useful because it converts causal to diagnostic probabilities and vice versa. Okay? So that's basically all is what I'm saying here. And then this is your definition of conditional probability. From that you get the product rule. And the product rule basically is also called the chain rule. And in fact, I didn't write the stuff that I said about Bayes' rule. There is no slide, but I'll write a slide. But you should remember this stuff what I said. And then finally, you should understand that probabilistic reasoning is more general than logic. So anything that holds in logic, you should be able to model it using probabilistic reasoning. Just a second. So yeah, but go ahead. Yeah.
Oh, I just wanted to clarify what you just said about the significance of Bayes' rule. Is it saying that since the word seemingly, I think you said.
No, so basically Bayes' rule helps you get, let's say, from a medical point of view, it helps you get probability of disease given symptom in terms of probability of symptom given disease times probability of disease by probability of symptom. That's just basically A and B being disease and symptom. Okay, and actually since you asked me, and there's so many things you can say. So ever since internet has become available, hypochondria is increased or reduced. You know what hypochondria is? I'm trying to help you with the GRE. Right? So hypochondria is assuming that you have every possible disease. Ever since internet has become publicly available, has hypochondria increased or reduced? Increased. How? You are having a slightly funny feeling, I'm having a slightly prickly feeling. And then I ask Google. And Google says, these are all the following various diseases, including, possible infection with Ebola virus that leads to this possible, prickly feeling. Then you say, oh my God, might as well just, what's the point in talking about take home versus in class? I'm going to be dead by tomorrow. So it's just end of the world. You start crying. Why do you do that? Because there is this issue, you saw this. I'm so sorry, you basically saw this. That if you have Ebola, you can get this symptom with pretty high probability. What you don't understand is the probability of Ebola virus infecting people in your neighborhood. You see what I'm saying? And so, actually, it turns out that if you are infected by Ebola virus, not only would you be getting prickly sensation in the teeth, you get a whole bunch of other things. And they'll all be with high probability, 1.0 probability more or less. But the probability that you are actually infected by Ebola virus, if you are a random person from Tempe, is maybe 10 power minus 9. You don't realize that because the internet doesn't tell you that. Do you see what I'm saying? So this, by the way, is called the fallacy of prior. Use the internet to figure out self-diagnose myself. And then mostly people go to, again, this is the other way doctors are making a lot more money with the internet. Because people come saying, doctor, I have figured out that I would be suffering from the following possible diseases. And if I am an enterprising doctor, I say, yeah, let's just get you checked for Ebola virus. That's just a $300 copay and $3 million test, but what the heck? I don't want to be sued. You understand what I'm saying? Okay, that's the thing. So you don't understand that. And by the way, this symptom business, probability of symptom business is also important. If there's a ice cream social, the probability of toothache, prior probability of toothache for this group of people, skyrockets. And you are dividing the total probability by the probability of toothache. You see what I'm saying? And so that's how Bayes rule makes sure that you come to the right decision. Okay. One more thing I want to do, given that I have this here, which is, even though I talked about the fact that the probability of symptom is basically probability of toothache, and essentially, that sort of changes if you are having an ice cream social, and you experience a lot of things. In general, computing this probability, this prior probability of symptom, in a kind of a medical scenario, imagine the medical scenarios, people write textbooks about what's the probability that a symptom will be caused by a disease. Because they actually studied, enough examples and they find these numbers. People also get a sense of, the doctors have a sense of, in a random population, what is the likelihood of this disease. What's harder is, in a random population, what's the likelihood of symptom. It's a harder thing to assess. Do you see what I'm saying? So the question is, can I avoid assessing probability of symptom? I want to use Bayes rule, but I don't want to get probability of symptom. I'll tell you how. You are trying to compute probability of disease given symptom. Right? And that is the rule. Suppose I also want to compute probability of not disease given symptom. Not disease given symptom. What would the rule be? Probability of not disease given symptom is probability of symptom given not disease times probability of not disease by probability of symptom. Do people see this? Right? Imagine I call 1 over probability of symptom, I call this alpha. Okay? Then essentially probability of disease given symptom is alpha times this numerator. Probability of not disease given symptom is the same alpha times this different numerator. Why am I doing this? If I add the probability of disease and not disease given symptom, how much should it be? 1.0. I add those two equations, I can eliminate alpha. Do you understand what I just said? People assume you understand this. In the next slide onwards, whenever I have to write this probability of evidence, symptom is the evidence. In general terminology, symptoms are